Let's start our 16th CRM camp seminar. It's my pleasure to have today Akitoshi Takayasu from University of Tsukuba. It's especially nice because he's a friend. He came to Montreal several times, and I was supposed to go to visit him in March, and the day before my visit, I decided not to go to Tokyo, and then for the reasons we all know. So that was my first trip, which got canceled, was to go to University of Tsukuba. So it's hopefully it will be postponed. Okay, so so Akitoshi Takayasu obtained his PhD from Waseda University in 2012. He was supervised by Professor Oishi, who's a pioneer in the world of rigorous numerics and differential equations. And so he also spent some time there as a postdoc at Waseda University. And after that, he got a position of assistant professorship at University of Tsukuba in 2016, and he's still there right now. And his research interests, they consist of rigorous numerics for PDEs, ODEs, delayed differential equations, and more generally, computer-assisted proofs in infinite-dimensional dynamical systems. So please, Akitoshi, go ahead and tell us about the hypergeometric differential equations in monodromy.
Okay, thank you very much for kind and detailed introduction. I'm Akitoshi, and today we would like to talk about computer-assisted results for finding the monodromy of hypergeometric differential equations. This is joint work with my former student, Naoya Inoue, and the PhD student in Chiba University, Toshimasa Ishige. Ishige is in this Zoom. We can see him. Okay, so let's start. This talk consists of three parts. First of all, we consider a monodromy problem. What is the monodromy and the main motivation of this project. And we discuss a slightly general approach for finding the monodromy. And actually, this is a linear differential equations, but we believe it is worth introducing in this seminar. Okay, and we use this approach for the two types of differential equations. The first one is the hypergeometric differential equation, which is very well known, and it is kind of a toy problem, but it is easy to understand, so that we would like to start from this equation. And after that, we would like to consider the Picard-Fuchs type hypergeometric differential equations, whose monodromy is not obvious, so that the result of computer-assisted proof is main contribution of this project. So let me start. So what is the monodromy is the start point of this talk, and let us consider linear differential equations in the complex domain. And now D is a domain of differential equations, which is not assumed to be simply connected. So this means this means that the differential equations has a singular point or a singular curve on which the differential equation is not defined. And we set a base point of the base point B, denoted by B in this domain. And we consider the fundamental group of the domain with the base point, so which is denoted by pi y of dB. And we denote the sigma by a loop in the domain, starting from the base point and ending at the base point. So this means that this loop is running around and back to the starting point, but that is the base point. And we also denote that the sigma aster. So this means the push forward of analytic continuation along this loop. And then by using this formula, we have we consider the analytic continuation of complex variable functions. And also, we denote phi of B is a fundamental system of solutions at the base point B. By using these notations, there exists a non-singular matrix, so M of M sigma. This is the element of complex general linear group, such that the pushing forward of analytic continuation of the fundamental system of solution is denoted by this formulation, so which is called the monodromy matrix. And if we consider the identity element from the fundamental group pi 1 dB, and then pushing forward of E star of the fundamental solution is the fundamental solution is itself. And if we take two elements from the fundamental group, phi and v, and we have distribution rule by using this formulation. So this means the identity element in the fundamental group is respect to the identity matrix in like this formulation. And distribution rule is also satisfied by using this matrix formulation. So this fact implies the monodromy matrix gives group homomorphism between the fundamental group and a complex generalized linear group. This is called monodromy representation of the fundamental group. And under the conjugate relation, the conjugate relation is defined by this relation, and any monodromy representation belongs to the same conjugacy class, which is uniquely determined by the differential equations. Then we call this conjugacy class the monodromy of differential equations. So the important point is if we have explicit formulation of the monodromy matrix, we have the monodromy of the differential equation. This is what we would like to show in this project. So anyway, so our main motivation is from this book. This is a book from Iwasaki and so on, and it published at 1991. And there is a definition of a monodromy problem. So for a given linear differential equation, find an expression of monodromy or find generators of the monodromy group with respect to the fundamental system of solutions. So this is a monodromy problem. And on the other hand, there are few problems which is whose monodromy is explicitly given, so that very restricted number of equations is not solved. A very restricted number of solutions only solved by using some analytical way. So that we believe that rigorous numerics help to find the monodromy for the differential equations in the complex domain. So this is our main motivation. And what we prove in this project, we prove two results of monodromy, finding monodromy problem. And first of all, we rigorously enclose the monodromy matrix for the hypergeometric differential equations. This is a slightly tough problem, but it is very easy and it is easy to understand. And after that, we obtain the monodromy matrix for a Picard-Fuchs type hypergeometric differential equations by using this formulation. So which is arising from a family of K3 surfaces. And so this is a topological surface polarized by a lattice. So this is our main target, main aim of this project. Okay, so let me introduce an approach for finding the monodromy. So first of all, we compute the value of fundamental solution matrix at the base point, the B. So we set the base point to B, we vigorously compute the value of fundamental solution matrix. So we say phi of B is in the element of complex general linear group. And when we consider the monodromy of differential equations, we consider the fundamental solution is a key point, but it is equivalent to consider the fundamental solution matrix. So this is why, so it is possible to consider the fundamental solution matrix instead of the fundamental system of solutions, because the space of solutions to differential equation is linear isomorphic to that of the initial values, so that we can consider the fundamental solution of a matrix. So it is isometric to the solution of fundamental solutions.
So
Okay.
let me ask a short question. So you see a fundamental solution, you can fix the fundamental solution at any specific point. So when you want to compute it at the point B, then you could, in principle, you could define it to be the identity at the point B. So there is not the fundamental solution, but there is concerning for every initial values, there is one fundamental solution. So which one are you considering?
So first we fix the base point B, and we take some fundamental solutions at B, at point B. So we take the value of the fundamental solution.
But in principle, you could take identity.
This is not a single solution. You know, the system of fundamental solutions, system of solutions, all the linearly independent solutions.
I can show you the exact.
Okay, I will wait.
Yes. Thank you very much. So, and after that, the second step is we set the loop sigma p in the domain and encircling the singular point at the p, and it's starting from the base point and ending at the base point. So this is the one loop, and we rigorously compute the analytical continuation denoted by this one. So using the rigorous integrator. So this means the initial condition of analytical continuation is denoted by the identity matrix. So then after that, we obtain the monodromy matrix using the following conjugacy formula, right? By using this formulation. So this formulation equal to the monodromy matrix. And okay, we would like to introduce more details of first for the hypergeometric differential equation. So we'd like to see the toy problem. Okay, so the hypergeometric differential equation is denoted by this differential equation, ordinary differential equations. We named the GH this equation, and we assume that the C parameters C and A and B denoted is assumed by this non-integer assumption. Okay, then the solution of hypergeometric differential equation is very well known, and it is denoted by a hypergeometric function, so which is defined by the power series, for example, like this formulation. And there are several regular singular points of the hypergeometric differential equation. The first one is x equals 0, and another one is x equals 1. The other one is x equals infinity. There are 3 points, 3 singular points. And for each singular point, we can define the fundamental solutions. So first of all, we consider the singular point x equals 0, and we take a domain of the fundamental solution, D0. We have 2 independent solutions. So there are two y01, y02 is two independent solutions of hypergeometric differential equation. So as we know, the hypergeometric function is a solution of hypergeometric differential equation in this domain. So there is another independent solutions. Okay, around the x equal 1, another singular point, we have another two solutions denoted by this one and this one. And we have two fundamental solutions in this domain. After that, around the x equal infinity, and we also have the two independent solutions, fundamental solutions, and formulated by this one and this formulation. Okay, and our target is to rigorously enclose the monodromy matrix by using rigorous numerics, so that we would like to consider the numerical approach. So first of all, we set the base point, now is a x0 equal 1/2, and it is in the intersection of d0 and d1. And we set the fundamental solution matrix phi of x0 is the element of a complex general linear group defined by this formulation. So this is this is what we call the fundamental solution matrix. And y0 is a fundamental solution around the x equals 0. I mean, around the singular point 0, and the other one is another fundamental solution. As we defined. Okay, so
Akitoshi?
Okay.
I have a question. So I think it was on slide 8, you assumed that a minus c was not in an integer, and you had some assumptions, and I don't understand why you had these assumptions.
Okay. So this assumption is related to the, for example, so this assumption, this one. Yes. So when this assumption is integer, so we cannot write down the fundamental solution by using this formula. So we needed to construct another power series.
Okay, but the fact that a minus c is not in z, isn't it too strong? Isn't it the fact that you want a minus c not to be equal to -1 or something? Or it's really, that was necessary, that they're not, okay.
But this is a technical assumption. So
okay.
Actually, yes. So
I think if you look at the Pochhammer symbols, then you see it, that it must be really as you pose it. Not equal to -1, but otherwise these things become, these Pochhammer symbols become singular.
Okay.
Yes.
Okay,
yes,
I see.
Thank you very much.
Okay, yes, that's right. Okay, that's correct. Thank you, Michael.
Yeah. Yes, thank you very much. Okay, so I would like to continue. Okay. So, yes. So and
I just ask a quick question.
Okay.
So there's this other version of the hypergeometric function, the sort of BOLDAF, that avoids a lot of these singularities. Is there a reason you're not using that version? So I think it's something like you multiply the hypergeometric function by gamma c or something like that.
But I just using this formulation now on.
Okay. Okay, because normally that simplifies things, but
yeah. Thank you very much. Okay, so and to compute the rigorous bound of the fundamental solution matrix by using this formulation, so we can have the derivative formulation by using this formula, and we rigorously enclose the phi of x0 using interval arithmetic. So of course we require the implementation of hypergeometric function, but there are still some libraries to implement such function. It's kind of a special function. Okay, anyway, we go further. We rewrite the hypergeometric differential equation as what is called the Pfaffian form. And the Pfaffian form is denoted by like this. And there is a matrix coefficient A of x. A of x. Oh, sorry. A of x. This is defined by this one. So we note that, so this is a non-autonomous system, so that it is slightly difficult to consider the rigorous integrator. Okay, anyway, so we set a loop sigma 1 encircling the regular singular point p equal 1, and we set the base point x equals 0, but which is 1/2, and we take sigma 1 as a circle and encircling the singular point like this, and rigorously integrating around this loop, we have the value of this one by using rigorous integrator. So anyway, and when we fix the loop, the sigma 1, the Pfaffian form is rewritten by this system of ordinary differential equations. And the initial condition of the ODE system is a 1, 0 and 0, 1. This means the initial condition is start from the identity matrix. And we rigorously integrate the system of ordinary differential equations from the t equal -1 to 1. And we have the enclosure of the push forward of analytical continuation along the sigma 1. And then we have a rigorous enclosure of the matrix, rigorous enclosure of the monodromy matrix by using this conjugacy formula. So this is what we did in this project. Okay, so this is a numerical environment. So we use some desktop in my laboratory, and I use a library for the rigorous integrator by the KB library, named the KB library. So this is a C++ numerical verification library developed by the Professor Kashiwagi. He's a professor in the Waseda University, and I think the integrator ODE solver of this library is the fastest one in the among the several ODE libraries, ODE solvers, and I like this libraries very much. And another point is we can use the interval. When we use the interval arithmetic, we use the double precision number at the end point of intervals. But if we don't have sufficient estimate for the interval arithmetic, so we can change such a number. I mean, the end point of interval is by some more multi-precision numbers. So this is easy by using the KB library, and we recommend to use the KB library especially in particular for the rigorous integrator. So anyway, so we set up the parameters a equal 1/2, b equal 1/3, c equal 1/6, and we did rigorous numerics. Okay, so before the result of our computer-assisted proof, we would like to show explicit formulation of monodromy matrix for the hypergeometric differential equation. So the M0 means the monodromy matrix along the singular point x equals 0, and M1 is given by this formulation, and M01 is called connection matrix defined by a gamma function like this formulation. But anyway, we have explicit formulation so that if we set parameters and we can get explicit value of monodromy matrix by using a numerical or some calculations. So now we consider the M1 matrix in this talk. Okay, so this is a numerical result. So first of all, we enclose the value of fundamental solution matrix at the base point by using these numbers. So this subscript, upper script means the end point and at the lower bound and upper bound of the interval. And we can get sufficiently accurate bound for the initial value, for the fundamental solution matrix. And we have the result of rigorous enclosure of monodromy matrix is given by this formulation. And the exact value of the monodromy matrix is like this formulation. And we have maybe 1, 2, 3, 4, 5, 6, 20 or 13 digits accuracy for the monodromy matrix. And the important point is we can rigorously enclose the explicit formula of monodromy matrix by using interval arithmetic, and the execution time is 1.6 seconds by using my desktop PC. Okay, so anyway, this is one toy problem. So I would like to show you what we did in this project. So let's go further.
Akitoshi?
Okay.
So the KV library, so I mean, I saw that your vector field, you integrated from -1 to 1. So I assume that you used Chebyshev series for that or not?
No, KV library used some power series. So this is a kind of Taylor series. So
okay,
just using, yes. And almost the same as the CAPD or another rigorous integrator for ordinary ODE.
Okay, so you did not use Chebyshev series to integrate at all?
No. So
okay,
actually, yes, there is a much of time-dependent term in this one, so that I cannot try Chebyshev in this program.
Okay, thank you.
Okay, so anyway, okay, so let's consider the second one. Okay, the second one is a Picard-Fuchs system of differential equations. So whose monodromy is not obvious in this problem. And the Picard-Fuchs type hypergeometric differential equation is denoted by this formulation. So we named this one is PF, like this. And okay, so that's PF like this. And now phi is a complex valued function from the C2 variables to the C variables. And there are a bunch of variable coefficients. So they are defined by these formulations. Now, X and Y is a complex variable. And and we have a much of non-autonomous terms in the PF differential equations. And actually, the Picard-Fuchs type hypergeometric differential equation is a partial differential equation with respect to the X and Y. And we have much complicated than the previous, the hypergeometric differential equation. And let me consider the Pfaffian form of this problem. And this Pfaffian form is called Morley-Cartan form. The Morley-Cartan form of the hypergeometric differential equations, which means which is denoted by this vector phi and phi sub x, phi sub y, and phi sub xy is given by this formulation. And now ax and by are defined by this matrix formulation. So also there are also bunch of differential no time to variable coefficients of B and C terms. And anyway, so we can see the so we can consider the Morley-Cartan form of Picard-Fuchs type hypergeometric differential equation. Okay, so before we consider the numerical approach, we would like to show you the topological background of the Picard-Fuchs type hypergeometric differential equations. This equation is derived from a two-parameter family of a lattice polarized K3 surface, which is denoted by y sub xy, defined by this formulation. So now f and lambda and mu is defined by this one, and y is the K3 surface is characterized by the periods, so which denoted by phi 1 and to phi 4, which is given by the integration of unique non-vanishing holomorphic two forms of a homologically independent two cycles, so which is denoted by this formulation. And now omega sub xy denotes holomorphic two forms over the two cycles, and now gamma I denotes the independent two cycles of the K3 surface. And we considering the differential equations with respect to these periods. We have the Picard-Fuchs type hypergeometric differential equation is obtained. And the important point is the monodromy occurs by deforming these two cycles. That is, by using analytic continuation along a loop sigma based on at the base point P0, and the two cycles in the K3 surface are deformed by using this formulation. So and here omega sigma becomes a unimodular matrix in the integer group, integer general linear group, and because these two cycles are basis, and M sigma is a change of basis matrix for the subgroup of second homology group, and this homology group is become the integer modular, so that our target is M sigma. This is a monodromy matrix, is integer matrix. So this is a topological background, so that if we rigorously enclose the monodromy matrix by using interval arithmetic, so we would like to show there exists only one integer in the interval. So this is a main target of this differential equation. Okay, anyway, so the fundamental solutions is much more complicated. Okay, we set a base point P0 by using a formula x0 and y0, and by parameterized the lambda 0 and mu 0 variables. The lambda 0 and the mu 0 variables are defined by 2 to the minus 10 value. And my collaborator, Toshimasa Ishige, provides for the following 4 fundamental solutions by using these power series formula. And phi 1 and phi 2 and phi 3 and phi 4, they are much, much complicated. But anyway, so these fundamental solutions are defined only this domain for the parameterized the lambda and the mu value, 2 values. And by using this formulation, I would like to rigorously enclose the value of fundamental solution matrix at the P0, at the base point P0. So by using a definition of this one. And now phi up k, to upper script k is defined by phi k lambda 0 mu 0. This is the value of the fundamental solutions that given by the Toshimasa Ishige. And by taking x derivative and y derivative and xy derivative of the fundamental solution, and we have a rigorous inclusion of the fundamental solution matrix at the base point. So by using the power series formula. And next, we consider the singular point of the PF differential equation. And now the PF differential equation becomes the singular locus, and the singular locus is denoted by these lines, by these lines. And thanks to the Zariski-Van-Kampen theorem. So this is the famous theorem in the topology, and without loss of generality, we restrict discussions on the plane, C2 plane, so such that denoted by L character. So this means if we consider the singular locus, we take one plane and we restrict the discussion and only one plane, and we can see the whole dynamics of complex differential equation. And we have 6 singular points. But anyway, so I would like to show you the pictures. And we consider the real x and real y axis. And for the imaginary axis, by using this formulation, we have almost same picture is obtained. Okay, on the real xy graph, the singular locus appears like this curve, and there are much of singularities around the 0 point, around the origin. And anyway, we take L line. Actually, this is L. Actually, this is L to C2 plane, but it appears line in this picture, and there for 4 singular points appear in this line, intersection of S and L line, and we named P1, P2, P3, and P4, 4 singular points. And there are another 2 points, complex numbers, so that we can see in this picture. But anyway, we have 6 singular points, and then we take base point around the regular area, and we take x0, y0 like this, and we would like to consider some loop around each singular point. Okay, so this is a loop of singular points, and which encircles the singular points, and we set the P0 as a base point, and we take a loop around each singular point. So for example, start from P0 and go to the around the P5, and we take one circle around the singular point P5, and we back to the P0. And this is a one loop. So this is a one loop of one loop for analytic continuation. And so by using this formulation, so in this talk, just consider the sigma 1 loop. So we start the P0 and around the P1 value, and we back to the P0 base point. So this is one loop. And by using this,
may I ask a question? So in your picture, can you please go back to the picture? So okay. In all other points except P5, you took the mathematically positive direction to go around the point. But in the picture, that indicates that you go around P5 in a mathematically negative direction. Is that correct, or is that a mistake in drawing?
Actually, it is not exact one. I mean that it's kind of a picture. I mean, so
go through also in the positive direction, right?
A positive direction, a counterclockwise direction.
Always counterclockwise.
Counterclockwise. All the loops are counterclockwise.
Then I expect. So in P5 it looks a bit as if it was clockwise, but that's just a drawing problem.
Yes, I'm sorry. Yeah. So just for the technique problem.
Okay.
I'm sorry. Yes. So I would like to show the result of our rigorous numerics, and by using the formula of fundamental solutions, which is denoted by the power series, and we take sufficiently accurate value of enclosure of the fundamental solution matrix by using this formulation. And actually, I skipped some subscript and superscript, so because we cannot see whole numbers in the slide. And anyway, so the result of analytic continuation times this conjugacy transformation is given by this formulation. So this means the M1 is an interval matrix. The middle point of the interval matrix is denoted by this one. So this middle point seems to be integer. It seems to be an integer, but the radius of the interval is too large. So that this means one element of matrix M1 has a midpoint is -1. The radius is 127. Also, there is no proof by using this result. But the execution time is almost 2.6 hours, and a huge error is accumulated. So why such a huge error occurred from this result? So this is because the scale of the differential equations. So for example, we consider the first row of fundamental solution matrix. So the first row is almost order 1, and the second row is almost order 1000, and the third row is 100. On the other hand, the first row is order 10 to the 7 or 10 to the 8. So that the scale of each row is different from each of them. So that if we consider the differential equation simultaneously. So we cannot, we lost the accuracy of numerical computation by this scaling. So that we would like to, we should more accurate computation for the rigorous integrator. So that we change the endpoint of intervals by using some DD arithmetic. By the DD arithmetic is a quasi-quadruple precision of numerical numbers, and by using this DD algorithm, DD arithmetic, we have almost same bounds for the fundamental solution matrix. On the other hand, the final result is changed. The final result is midpoint is same. It's kind of, it seems to be a integer matrix, and the error bound is to 10 to the minus 8 or 10 to the minus 6, so that we complete the proof. So there exists one integer in this interval, so that each element is -1 and -2. These elements are the exact value of a monodromy matrix. So this is a final result, and it takes 5.6 hours by using my desktop PC, and anyway that we complete the proof. Okay, so we would like the summary of our rigorous result by using a rigorous numerics, and we find the monodromy of Picard-Fuchs type hypergeometric differential equations. So M1 is a it's a monodromy matrix around the P1. I mean the singular point P1. That is we considered in this talk, and that is explicitly given by this matrix. And M2, M3, M4, and M2, M6 is given by this formulation. So this matrix representation is proved by our approach via the rigorous numerics. That is the result of a computer-assisted proof in this talk. Okay, that is all. Thank you very much.
Thank you. Thank you very much, Akitoshi, for a very nice talk. Are there any questions or comments?
So maybe I have one. Hi, Akitoshi.
Yes, Maxime.
Hi.
So in the previous slide, when you have could you explain a bit more what is behind this computation for which you have the large error? So what exactly is the computation that you need to do here? I didn't quite follow the.
Yes. So actually, the scale of each row is different. For example, by considering this column, so this first line is almost 1, and third line is and first three rows are almost same order. On the other hand, this row is 100, so that there is some difference from
scale,
the different scale. With the most one is this one.
Yeah. So I guess my question was sorry. So the sigma 1 star here. This is what you have to compute. What is taking all the time, right?
Yes.
How exactly? What is? Could you recall what is this for this problem and how you compute it? So this is related to the PDE you showed at the beginning, I guess, right?
Yeah. Okay. So I tried to explain. So when we set a loop around this one, so we explicitly expressed the loop by using some time t by x sub x of t and y of t, and by using this formula, so by using this formula, this Morley-Cartan form is changed into the system of ordinary differential equations.
Okay.
Yes, so that we
Okay,
rigorously compute from the initial point, go to the back to the end point.
Okay, I see. Thank you.
But the important point is this is not a boundary value problem. So because there is a singular point inside the loop, so that the solution is not solution is changed back to the same point.
Okay, thank you.
Okay, other questions, comments?
So I forgot, are there parameters in the equation which you have fixed to a certain value? Is that right? Or is the equation free of parameters?
Yeah, actually, just a moment.
So I forgot the formulas for the P, A, B, and Q, C, D, and M.
Yes. So now my computer is freezing. So that's just a moment. Just a moment.
Parameters have
Previous
been
slide. Yes, previous slide. I can see. I can show
freezing parameters is sometimes a good idea.
Okay. Yeah. Yes, this one is a explicit formulation. So these are
no parameter.
No parameter. Yes. Variable coefficients.
Okay, if you have no parameters, then my question is redundant.
No, okay.
So I have a question. So you mentioned before that you're using the KV library and which is based on a Taylor expansion, and then you said that Chebyshev in that case was not really possible because of the form of the non-autonomous terms in the ODEs. And is that the only obstruction, or there's something like that I'm missing that would prevent really Chebyshev series from being useful? Because the fact is that you're doing line integrals, and then you want to go around singularities, and your Taylor series will have domain of convergence. Restricted by these singularities, and Chebyshev could somehow probably, because you're parameterizing that by real parameter, right? So
yes.
So then you would have like real functions in with values in the complex plane. So at first, it looks like Chebyshev series could be doing a great job of approximating the solutions, or not.
I think it is possible. I mean, actually this around on this loop, there is no singular point. So I avoid the singular point so that it is very smooth solution appears. I mean, actually, it's an analytical function. So that if we work on seriously, so we can apply the Chebyshev series for this type of differential equation.
Yeah, because I actually have some similar problems right now. I'm using some line integrals in the complex plane, and I'm using Taylor right now because it's convenient. But I need to do a lot of initial value. I need to do a lot of rigorous computations on small little balls to cover a path.
Yeah.
Because of I'm also kind of going around loops that contain singularities, and sometimes the balls are getting quite small on which the Taylor series are converging, and I'm thinking of doing one or two line integrals with Chebyshev, and I think that numerically it would be a tremendous benefit. But yeah, I mean, now of course the formulas may be a bit more nasty, but once you figure out the math, then maybe it's a big improvement.
Yeah.
Okay, but you did not, because when I saw that your time interval was from -1 to 1, I really thought you were going to use Chebyshev, but not. Okay.
I think that the question is related to the question, how much is the error accumulation during the integration process? I think in the Taylor approach, you might have error accumulation, and with the Chebyshev approach, you can avoid it. I think if you have a lot of error accumulation during the process, then the Chebyshev might be better.
Yes.
It's my impression.
Sorry. Yeah.
Okay. Yeah.
No, I most definitely. Yes.
So is there a lot of error accumulation in your integration process?
Yes.
Yes. So
much accumulation.
Yeah, then perhaps Chebyshev would be easier. Anyway, okay, you have got the proof now, so it's not needed to change it.
Yes. Yes.
Maybe for other examples.
Yeah. Yeah.
Okay. Thank you, Akitoshi. Are there other questions? So, well, I mean, maybe I will ask. No, so no more questions. All right. Well, then in that case, let's thank Akitoshi again for a wonderful talk. Thank you very much, Akitoshi.